Hello everyone, welcome to Azure Cosmos DB Con 2024. Myself Divakar, I work as a technical architect at Flyosoft. Today I will be covering on a topic on how to build a RAG-based LLM application with the help of Azure Cosmos DB's native vector search capability. If you are familiar with the technical landscape of the ChatGPT, you should be aware of this question. What is the database behind the ChatGPT? It is the Azure Cosmos DB. That is for one of the many reasons why you could see the ChatGPT platform was able to scale up to millions of users without any issues. And apart from the common benefits of having high scalability and performance, the Cosmos DB team has also introduced us with vector search capability for two of its APIs. One is the MongoDB vCore API, and the other one is the PostgreSQL API. If you are relying on the NoSQL API, you should be having a separate vector database. It could be a search as well. But sooner or later, like we will be having an integrated vector database for the NoSQL API as well. But before getting into the benefits of the vector search capability, let's try to understand like why do we need a vector database in the first place. So whatever the generative AI models that we have right now, whether it is GPT 3.5 or the GPT 4 models, all these models do have a context window, a token limitation beyond which it wouldn't be able to respond as back with a natural language response. To, to put it in a simple term, you can't dump everything into this LLM and expect a response back from this model. You need to effectively retrieve the relevant documents and then feed into the LLMs so that it is within the limits of the token consumption that it has, the context window, and it will be able to respond us back with the natural language. So in order to do that effectively, you need to store the vector representation of the data in a database and then do a similarity search on whatever the query that you posed by the semantics of it. You need to retrieve the documents based out of it. So that is the main reason why we are looking out for the vector database in the current phase of the LLM applications. So these are some of the advantages that we get out of the MongoDB vCore. So now we have the native vector search capability as we have discussed already. What that means is like now you have this vector embeddings alongside your operational data. And one of the cool things to note here is like whenever you do a transaction on the operational data, you could create the embeddings of those data in the single transaction and then commit them in the single collection. So if you were supposed to use a separate vector database, then what you would have done is like you need to make sure you are not referring to the stale data. You need to come up with a schema, come up with a practice to whenever like there is an update in the operational data, the equivalent data or the representation of the data is updated in the vector database as well. But in the case of Cosmos DB for the MongoDB vCore, whenever you update the operational data within a single transaction, you could update the embeddings and then store them in a single database. So for that reason, like you can keep the cost-effective solution and then keep the solution more simple. But obviously, the AI search is also gonna have some advantages when you want to have multiple data sources and then try to create the embeddings of those and then effectively retrieve from those multiple different data sources. You could still preferably go for AI search, or else like if you want to do semantic ranking and then do a hybrid search on top of your data, you could still prefer to go with the AI vector search. But for our use case, like whatever we came up with, we found the MongoDB vCore with the vector search capability was a better use case for that. So who would be the right target audience for this is obviously if you are an existing customer of the Cosmos DB who are currently using Mongo API, you could still use the vector search capability of the MongoDB vCore. And if you want to work alongside your operational data, as we discussed earlier, you could still make use of this MongoDB vCore. And if you want to improvise your RAG-based applications by uh, not frequently making an LLM call, rather than like uh, fetching the response from the persistence layer that you have within the Azure Cosmos DB, you could do a semantic hatching by converting the query into the vector representation and then doing a similarity search on the database, then fetching the response from the database rather than getting the response from the LLM. So this avoids unnecessarily latency because it is going to be the same query which is being asked by multiple users. So you could improvise this pattern by introducing a semantic catching with Azure Cosmos DB. And finally, you could build a robust feedback system. Say, suppose it is not going to be a challenge on building a LLM based application. The main challenge is like how you are going to evaluate those models because sometimes these models could hallucinate and it could respond you back with some random response apart from your grounded data. So how do you make sure that it is responding us back with the grounded data? Is something like that you need to improvise in your prompt engineering or in improvising your data quality. For you to do that, you need to understand like what are the different prompts that you are receiving into your system and then analyzing those with the help of human in the loop. To build those things, the Azure Cosmos DB will be playing a major role. So we came up with an simple use case for building this LLM application. So this is the entire architecture for our application. So what this is a simple use case. Like whenever a client is gonna post us with a requirement, the HRR manager is gonna use this Copilot app to effectively drill down into an employee who will be a best fit for those requirements. So in order to do that, we went into different phases of this architecture. Let me start with the prerequisite phase. As you all know, like in the service-based company, like across the organization, we tend to follow a specific template for the resume. So what we did is like we collected some of the resumes from the employees and we started training on those documents. So what we did is like we labeled those documents and we created a custom abstraction model from it with the help of Azure Document Intelligence Service. So once we did that, as a final output, what we get is like the all the relevant contents from the resumes will be received in a JSON format. This is how it looks like in the Azure Document Intelligence Service. So in the first place, we started by labeling those documents by having the field name and the respective field value. As you could see here, the employee ID, the name, and then the table matrix are mapped with the respective fields and the values. So once we did this for few of the employees, we started training on those documents. So once the model is generated, we can test this in the Azure portal itself. By doing this, you could see in the right pane, you could see the JSON response from this Azure Document Intelligence Service. So this will be used in the later phase of our architecture. The next phase is the core phase of our application. So whenever a new employee is going to onboard into the organization, or if you want to upload the documents, these documents will be getting into the Azure functions. We hosted the Azure functions in the container app environment, uh, which is represented as blob processor here. And this storage and equivalently like it will place a message into the service bus. This will kick in the process of the worker service. So this worker service will keep on listening to this service bus message queue, and whenever a message has been placed, so it picks up the resume document from the blob storage and it will feed it into the Azure Document Intelligence Service. So from the Azure Document Intelligence Service, we get the response back in a JSON format, and we start doing chunking of those documents because it is going to be a long document, the response that we get from the document intelligence. And we will be seeing in deep on how to do this chunking in the next few slides. So once we did this chunking, what we did is like we want to create a vector representation of those data. So in order to do that, we made a call to text embedding ADA model from the Azure OpenAI service that converts the data representation into the vector format, and we stored them in the Azure Cosmos DB. So as a prerequisite, like we already created a vector search index for the vector field, and now these vector data is all the chunked vector data is all stored in the Cosmos DB. The next part is like whenever an HR or manager is gonna use a basically it could be a requirement from the client. So this requirement from the client will be converted into the vector representation using the text embedding ADA model, and we do a similarity search on the Cosmos DB. So this similarity search can be done in several ways. You could use different algorithms. In our architecture, like we used IVF, inverted file index algorithm for doing the similarity search. You could also use HNSW, which has been available in the MongoDB vCore, which we will be seeing in deep in the coming few slides. So once we did this similarity search, we retrieve the relevant documents from the Cosmos DB, and we only feed those relevant documents into the GPT 3.5 turbo model. This is the model that we use to generate the final response in the natural language way. So we use GPT 3.5 turbo model, and we only post them with the relevant documents, and the final output will be sent back to the chat application. So this is going to be the entire flow of our architecture. So in order to do chunkings, there are different patterns out there. If it is going to be a simple use case, you could still prefer going with a fixed chunking, or you could prefer going with a fixed chunking with the overlap if you are worrying about like losing the context. Or if you want to have a better way to do this, you could rely on the semantic chunking. So how we did the semantic chunking is like whatever the JSON document that we get from the Azure Document Intelligence, we have several properties like employee ID, name, summary certifications, achievements is past experience, and then the projects that you worked upon. So what we did is like we created chunks which felt most semantically clubbed together. Like we want to club together few of the properties so that it would be used better in the retrieval process. So all these chunks will be having metadata, which is going to be the employee ID or the name. So we stored this employee ID and the name in all of these chunks, so that like in the final response you will be getting to know like which employee it is referring to. And along with that, like you could now have the better control on how to do a semantics separation of these chunks. And as an optional one, if you feel for certain properties you need to do the summarization because it contains large amount of text, you could do summarization on top of it using the GPT 3.5 turbo model, and then feed it into the test embedding data model. So now what we did is like we had a refined rack model, because now we did the semantic chunkings, and we have only the relevant semantics clubbed together as a chunks, individual chunks, and these get into the Cosmos DB as the vector embedding. And coming to the vector search, uh, this is how it looks behind the scenes. So these chunks of the documents, what we did in the previous phase, will be fed into the text embedding data model to generate the embeddings of it. This is nothing but the array of node, which is a vector representation of those data. It will be stored into the Azure Cosmos DB for MongoDB code. So here we have already created an index and a respective field for it, where we will be storing this vector embeddings. So now whenever an HR or manager is going to post us with a query, the query is going to be equivalently translated into the vector representation using the same model, the text embedding data model. And we do a similarity search using the IVF algorithm. So once we do the similarity search, it brings the nearest neighbor, like whatever is semantically meaningful for those queries, and it will provide you when while you are doing the vector search. So this is how it looks like in the documents. Each of these chunks are stored in individual documents, and you could see now you have the operational data along with the operational data along with the vector representation of those. So now that we have done the semantic chunking along with the refinement of the RAG flow, so we were able to see a tremendous improvement in the token consumption. Earlier, like when we post with a query, it was using till the maximum limit of the token because we didn't do the chunking part, and the entire vector representation was stored in the same collection as the operational data. And once we did the semantic chunking and refined those RAG flow, we were able to reduce the token consumption up to 1986. So that is the improvement that we have made with the help of this semantic chunking. And also while doing the vector search retrieval, earlier like we weren't able to retrieve the correct information from the application because it always hold the information up to till the maximum limit of the token. So it was holding only the information of the first employee. It was not holding the information of other employees. So whenever we asked about a question about a random employee, it couldn't respond us back with the employee detail. Rather than it just said it only has the information about the employee X because it would have reached to the token consumption. So that was the response that we got before doing the refinement of this RAG process. And after we did the semantic chunking, we were able to retrieve the employees who were uh, able to handle this requirement in an effective way. So this is how we were able to make use of this Azure Cosmos DB's native vector search capability to improve our vector improve our workforce efficiency. That's all I had for this talk. If you have any queries, you can always reach out to me on the LinkedIn channel. Thanks.